So I'm going to do this, the next bit in this chapter, the last bit more or less, not the way that he does it. So, because I'll do it, give my proof as it were. Thing that I'm comfortable with. Okay, so what we wanted to prove last time was that suppose you have sigma weekly continuous star homomorphism. One usually refers to when talking about one-level algebras, such a mapping one is usually calls simply a normal representation. Representation always refers to a mapping structure preserving homomorphism into operators on Hilbert space or a vector space, or so in our context always Hilbert space, and the normality refers to this continuity in the sigma vector polynomial. So given any such homomorphism, we wanted to say that pi m is a one-level algebra. The C-star algebra version last time was that any homomorphism of a C-star algebra, the image is star closed. That is the argument that I went through last time. I didn't quite complete it, but I made some fuzzy analysis about ideals and so on. But so at least the one-level case will prove completely and rigorously. Okay, so let me call this thing as n. Then what we do know is M is also a C-star algebra and pi is a C-star algebra homomorphism. So the image is a C-star algebra, and the pi is going to map the unitary. We know that any C-star algebra homomorphism is always contractive. Right? Norm pi x less than or equal to x for all x. That means we know that pi of the unit ball of M will be contained in N. Because all C-star algebra homomorphisms are norm decreasing. So if our goal is to prove the reverse. If I prove the reverse, it will show that the unit ball of n, being a sigma weakly continuous image of a sigma weakly compact set, it will show that the unit ball of n1 is sigma weakly compact. And hence, and that was one of the characterizations of one-Neumann algebra. That means n is a one-Neumann algebra. So it is enough to prove that prove the reverse. Okay, so what do we do? So we take so let y in n1 then there exists, by definition, there exists an x in M, so that y is pi x. Of course, x may have large norm. For example, y could be 0, and x could have been anything in the kernel of pi. So you have no control over the norm of x approximately. But what we will do is to doctor this x to get something of norm less than or equal to 1, which also gets mapped to y. Okay. What is clear is that because pi is the star homomorphism, that pi of first pi of x star x equals pi of y star y. That means pi of mod x, the whole squared is mod y squared. So by uniqueness of positive square root, it will follow that pi of mod x must be mod y. Right? Okay. So I'm not writing all the word things I just said now on it. So that will mean that, of course, that what will it mean? It will, see, I want to pay attention to pi will map will be contained in W star of mod y. And we know separately that each of them looks like L infinity of something. And so let me start again. I'm restricting attention of pi to this singly generated one-Neumann algebra. So this noise I've made about C-star algebras before. If you have a representation of a C-star algebra, if the C-star algebra is singly generated, then it is completely determined by what it does on the generator. Like groups. homomorphism on a cyclic group is completely determined by what it does on a generator. So I want to say that, see we have pi doing this and sending 1 and x to, it sends 1 to 1 and mod x to mod y. Okay. So we know what W star of 1 mod x looks like. This is by definition all things of this form. F in L infinity, or let me just say F bounded measurable function. Spectrum of x. Then you don't have to look say L infinity. Anything in L infinity is equal almost everywhere to a bounded function. So the f of mod x is the same as a bounded function of mod x. So this is really just a set of all bounded measurable functions of x, mod x. In a group, for example, if a group is cyclic, the elements of the group are exactly the powers of the generator. If the generator x goes to y, then x power n must go to y power n. And similarly, so what I want to say is that I want to say that pi of f of mod x one minute. We have a spectral inclusion, right, between mod x and mod y. Right, we show that if you have homomorphism pi from here to there, things which are invertible here will be invertible there. That means if it's not invertible there, it's not invertible here. So the spectrum of that is contained in the spectrum of this. That means we know that the spectrum of mod y is contained in the spectrum of mod x. So I want to say that for all bounded measurable functions f on sigma mod x, I can make sense of this, and so what should be the natural answer to be expected? Then it should be the same function of mod y. F sends mod x to mod y, so it will send polynomials of mod x to polynomials of mod y. So this is clearly true for all contiguous functions. Okay. And given any, so I must have mentioned this before, but I'll just repeat it. Given any bounded measurable function on a compact subset here In fact, it can be any compact subset of any Rn. Given a bounded measurable function, the point is that continuous functions are dense in there's something called Lucian's theorem, which says that any bounded measurable function is going to be agree with a continuous function outside a set of small measures. If you give me an f, I can find a continuous g, and if you give me an f and if you give me an epsilon, I can find a continuous g such that g agrees with f outside a set of measures smaller than epsilon. So that is what Lucian's theorem says. Now, from Lucian's theorem, it is not hard to verify. Let's say this the consequence of Lucian's theorem. Given such a bounded measurable function, I want to say there exists almost everywhere. There is a almost everywhere statement any. So what I'm struggling to say is the following thing. See, if there's only okay, see, if you're given one measure mu, so the reason I'm kind of struggling is the following thing what is true. You know that W star of mod x, mod x if you wish, looks like L infinity of spectrum of x with respect to some measure mu. Okay. Similarly, for y, this will be for some other reason new, whatever. But what I want is the following, and given any measure, so for example, I will take the measure mu plus nu. Nu is a measure on the smaller set. I can take mu plus nu restricted mu on the smaller thing. I can look at the measure lambda, which is okay. So for one function, let me say the following thing. Here it is on sigma of mod x, and so that I measure mu. Okay. So I want to say there exists a sequence of continuous functions. which are uniformly bounded. I can choose them all to have norms smaller than the norm of F. Here by infinity norm I just mean the soup. They are actually bounded function, there is no null set or anything, just soup norm. I can find such functions such that Fn converges to F mu almost everywhere. And you just need to use the fact that okay, Lewis' theorem is what you need to prove this thing. You can use it. So let me leave it with it. See, why am I saying all this? See, we know that. See, the equation that we want to prove, star is clearly true for polynomials because pi sends mod x to mod y, it will certainly send polynomials to corresponding polynomials. And then by Weierstrass, it is also true for continuous f. Because pi is a non-continuous. And now I want to say from this that, see, pi Fn converges to F mod x SOT. That's what we proved long ago, if you remember. If you have functions which converge like this, if you have bounded continuous functions which converge almost everywhere, then the Fn of mod x will converge in strong operator topology to F of mod x. So this is true for any measure on spectrum of mod x. So I can take a measure which is, for example, I can define lambda of E equals mu of E plus nu of E intersect spectrum y. Then I can do the whole thing, I can say lambda almost everywhere. It is true for any one measure that you want to take. But then if it happens lambda almost everywhere, mu and nu are both absolutely continuous with respect to lambda. There is lambda null sets, will be mu null sets and nu null sets also. That is if they are inside this thing. So what I am saying is that, so why I am saying all this is that if I say it this way, then I can conclude that also Fn of mod y will converge SOT to F of mod y. So it is also WOT. But this mapping pi is sigma weakly continuous. So on bounded sets, it will also, that is the same as WOT continuous. Now all these things are in a norm uniform. The norms are all uniformly bounded. So all the Fn mod x's are uniformly bounded. So Fn mod x converging WOT is the same as saying Fn mod x converges sigma weakly to Fn mod x. And similarly, Fn mod y converges to F mod y sigma weakly. So, by this argument, this is true for all bounded measurables. And so I'm just saying that the natural one has to do all this fancy footwork to prove this perfectly natural sounding thing. Okay. So now let's get back to what we were trying to prove. We started with the y in this n. With norm x equal to 1. But that means mod y also has norm less than equal to 1. Because mod y and y have the same norm. If mod y has norm less than equal to 1, notice that mod y is a positive operator, it has norm less than equal to 1. That means what can you say about the spectrum? Where is it sitting? So the spectrum of mod y is contained in 0, 1. Right? So the spectrum of mod y is contained in 0, 1. Okay. Now we have this functional calculus for bounded functional calculus for mod y. So what is 1 sub 0, 1 of y, mod y? Huh? This is a projection. The functional calculus is the identity operator, right? So this is the identity operator on the K. So what does this say? This thing will tell us that, but we know that pi of f of mod x equals f of mod y for any bounded measurable function. So let me take f to be indicator 0, 1. Actually any indicator E. Then this says that pi sends indicator E of x mod x to indicator E of mod y. That is, it says that therefore pi of indicator 0 1 of mod y mod x equals identity. Also, pi of identity of the Hilbert space is identity of K. We assume that pi is a unital homomorphism. See, mod x might have some large norm. See, suppose if mod x had that norm less than or equal to 1, then we don't have anything to do. Because you would have found something in the unit ball which gets sent to that mod y. And then I'll use polarity composition to show that y is the image of something in the unit ball. So, suppose the norm of x is some alpha bigger than 1. So what this will say is that pi of this must be 0. Because if I add the indicator 1 alpha to 1 0 1, I'll get 1 0 mod alpha, 0 alpha. Pi of the 1 sub 0 alpha of mod x will be identity. Already pi of 1 0 1 is identity. So this extra piece must be 0. So what does all this mean? That means if I take, say suppose x has polarity composition u mod x. Then this says, and the y will be pi x, pi u, pi mod y, pi mod x. But see, as far as mod x is concerned, see mod x See, mod x corresponds to the function t on 0 to alpha, or inside there, whatever the spectrum of mod x is. Now, but pi of see, this is 1 of 0 alpha of mod x times mod x, and because this is the identity. Because norm x is alpha, 1 sub 0 alpha of mod x is the identity. But by what you've shown here, this is actually equal to 1 sub 0 1 of mod x times mod x. 1 sub no, they don't what I want to say. So I'm saying let x1 be this. Let x1 be not this, be u times this. Because x was u times mod x. But the part of mod x which was bigger than 1 was being killed by pi. So I want to take x1 to be u rather than mod x. I take mod x times this position. Now I want to say that y equals pi x1. What is the difference between x1 and x? See, x1 minus x equals u times 1 0 all sometimes let me look at x minus x1. So here I have mod x is u 0 alpha mod x times mod x. So u mod x is this thing. So this is what x is and x1 is this thing. So x1 minus x is u times this minus this will give you exactly one sub 1 alpha mod x times mod x. So if I apply pi to both sides, in the middle I'll have the pi of 1 alpha mod x, but that fellow is 0. So the conclusion is that therefore pi of x equals pi of x1. Now pi of x was your y, the y you started with. Now what does x1 do? x1, I'm saying the norm of x1 is less than or equal to 1 because this corresponds to the function mod x corresponds to the function t. So this thing corresponds to just the function t on the unit interval. That is what this whole part is. So this whole operator has norm less than or equal to 1. Because there is a functional calculus applied to that function which is t on the unit interval. Intersect this vector of mod x. And u is a partial isometry and has norm less than or equal to 1. So we find that norm of x1 is less than or equal to 1 and pi x1 is y. Finally, we proved that in fact anything in the unit ball of the image in that n is actually the image of something in the unit ball of n. See, working with this functional calculus is really the sense of understanding positive operators. And then using a polar decomposition, there is a way to really study all operators more or less. So as a one justification of the all operator statement, let me give you a proof of this fact that he gives in that is given in the book here. But not the proof, but the proposition is following. So M is the phenomenal algebra. We know that the unit ball of M is sigma weakly compact. So, and of course it's convex. It is a compact convex set in a locally convex topological vector space. There is, in a vector space where the topology is given by semi-norms. And in such spaces is exactly where the Klein-Milman theorem comes into effect. It says that any compact convex set is the closed convex hull of its extreme points. You all know the Klein-Milman theorem? No? Sorry. See, the Klein-Milman theorem in a sense, this is the key to doing most optimization problems. Meaning, usually you have some. So I'll come back to this. Okay, suppose I have some. So I'll only look at nice sets like this, which are compact and convex. And suppose you are given an affine function, that means like a linear function, there is something which respects convex combinations. So suppose you are given a function phi, which is affine. That means phi of tx plus 1 minus ty is t phi x plus 1 minus t phi y. Or may not even be affine, maybe one is only looking at a convex function. Convex means you have a distance. And the problem is to, let us call this compact convex set K. The problem is to find if we take a convex, then I want to optimize, I want to find the supremum of phi x, x and k. And I've given you a very general problem. So to find the maximal value of this function on this convex set. But now, because you know that it is convex, notice that whenever something can be written as a convex combination of 2 points, the value there cannot be more than the value at one of these, at the maximum of these two. So what this will show is that this is actually equal to, in this case, if you take these 5 points, these are the so-called extreme points of the set K. In fact, more generally than this, you have suppose you have phi of summation Pix less than equal to summation Pi Px, where Pi are non-negative and summation Pi is 1. Such a thing is called a convex combination. If you take a convex combination of points, now one can actually show that in a silly example like this, any point inside this pentagon is expressible as a convex combination of the 5 vertices. So the maximum that phi can take anywhere inside the set, if phi is going to be convex, has to be only at one of these 5 points. So to find the maximum, it is enough to look at the maximum over those extreme points. So the thing that distinguishes these points is that they are extreme points. So we usually be interested in compact convex sets. You can talk about this distortion more generally. We'll say that Z is extreme or not extreme if you can write Z as, let's say, an average of two things with Z not equal to Xj and K. If I take a point here, for example, I can certainly find a small little line segment whose midpoint it is. So no such point will be, every such point is non-extreme. To say extreme means not extreme. That means you cannot express it as an average of 2 points. That is the same as you cannot express it as a convex combination of points which are distinct from it. So in general, convex sets can be quite complicated. So even in finite dimensions, if we take the unit disk, that is a compact convex set, but it has infinitely many extreme points. You cannot say that everything here is a convex combination of extreme points. You will have to take limits. So the right thing to do is to take the closed convex, by a convex hull of a set, you mean the smallest all convex combinations of points in that set. The closed convex hull is the smallest closed convex set which contains all those points. So let us denote that by this symbol. Closed convex hull. Okay, Klein-Millman says the following thing. If you have compact convex set in a locally convex, that this means a vector space, topological vector space whose topology is given by a family of seminorms. That is the kind that we've been talking about. Given any such thing, K is the closed convex hull of, I will take this is for, this symbol I will write for the set of extreme points of K. It is some kind of a boundary, that's why it is the boundary operator symbol. So del E of K is the set of extreme points. So in general, wherever this already shows that, if you are given a compact convex set, it is important to know in many situations like this just what the extreme points are. For all such optimization problems, that is a natural thing to look for. So what I was going to say was that if you have a one-Neumann algebra M, you know that its unit bond is sigma weakly compact. So M1 is a candidate for one of these Ks. So I can want to find out what are the extreme points of the unit bond of M. X is the extreme point of the unit ball of M, if and only if this, what do you think the answer will be? Look at finite dimensions. So what do you think are the extreme points of the matrix algebra, of the unit ball of MNC? Huh? All Neumann things.
Norm of x is equal to 1.
So if I take a projection, if I take the matrix which is, so I take n-man matrices, I take a projection on, not projection, norm 1 you say. So Yeah, this is actually confusing counterexample, but nevertheless, norm 1 means in the 2 by 2 matrices, this has norm 1. Right? And so does I put plus or minus half in the bottom diagonal. That also has norm 1, and the average of these two is this. So this is not extreme. In fact, one can show that the extreme points of the of MNC is exactly the unitaries. Actually, that's a good exercise. You should be able to prove that. So, since we've gone into the digression, might as well do it properly. So let us take M equals MNC or B of Cn or whatever. And I want to look at what the extreme points of M1, the unit ball of M1. So again, this is a typical example of how you use the two fundamental theorems I've been trying to peddle to you about operators is the spectral theorem and the polar decomposition. The spectral theorem deals only with positive or normal or something like that. But for the general operator, you have to go use the polar decomposition to kind of try and reduce to positive things somehow. Okay. So let us take an x in M1 and let us look at its polar decomposition. Okay. See, first I want to say, and suppose x is actually an extreme point of F1 and look at its polar decomposition. So I want to say you look at the polar decomposition of M, that's what you've taken. Right? Now since you are in finite dimensions, the support of mod x and the support of mod x star have the same dimension. So in fact, because you are in finite dimensions, this x has such a polar decomposition where the u can be chosen to be unitary. And so let us consider cases. So case 1. I don't know. So I claim that mod x must necessarily also be an extreme point of a mode. Mod x is on the unit ball. I want to say it is an extreme point. First, it has a polar decomposition with u unitary. If mod x is not an extreme point, if mod x is an average of two contractions, if mod x is x1 plus x2, a1 plus a2 by 2 with the a's having norm 1, then I can take ua1 plus ua2 by 2, that will give me x. And ua1 and ua2 will have norm 1. Okay. So through the polar decomposition, we found that here, because it was actually unitary, we found that the mod x must be an extreme point. Now, which mod x's can be extreme? Mod x is positive. Positive means spectral theorem. This is what we have to use. What is spectral theorem at finite dimensions? Mod x can be written as a diagram. So mod x I can assume by that means the unitary is add u of mod x is diagonal and add u is the automorphism. So mod x is diagonal is the same as saying that add u of mod x is diagonal. And mod x is extreme is the same as saying add u of mod x must be extreme. So you can assume without laws of generality that mod x is actually diagonal. If mod x is diagonal, what you told? You told that what does this statement mean? It is an M1. What does it mean about the alphas? A finite number, there are only finitely many alphas. So each mod alpha j is less than or equal to 1. Okay. Can alpha 1 be half? Can you rate half as an average of two things between 0 and 1? You cannot rate half as an average of two things between 0 and 1. If we take any alpha, if any alpha j is in the interior, then of course I can write it as a midpoint of two things. That means just in that coordinate alone you write it as those things, keep everything else the same, and you'll see that in fact to even say that m plus 1 if and only if all alpha j. So what does it say about alpha j? No alpha j can be basically what are the extreme points of 0, 1? It's just 0 and 1. So that means all alpha j must be 0 or 1. That's what this says. That means that everything must be 0 or 1 here, and but you can do out the 0 thing because you're in Mn. So what I'm saying is, if alpha 1 is 0, see, even if x, I can write this as it is an extreme point of positives. The unit bar of the positives, if it on leave, they are all 0 and 1. They are all 0 or 1. If and on leave statement. But I'm saying conversely, if some alphas are 0, let me ask, when is a self-adjoint element an extreme point of M? When can a self-adjoint be extreme? Self-adjoint means it is just, these are all real numbers between, here they were all between 0 and 1, they were in the unit interval. But now you are in -1 to 1. So every alpha j must be +1 or -1. So what I'm saying is, if one of these was 0, I'm just making the simple binary statement. If you take 0, blah, 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 I can write as half, blah, 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 plus minus half, blah, blah. That is still an expression of that self-adjoint of mod x as an average of two self-adjoint contractions. But if I can write mod x as a1 plus a2 by 2, where the a is the self-adjoint and norm less than or equal to 1, then still I can write x as ua1 plus ua2 by 2. So I'm saying, in order for this x to be extreme, in fact, no alpha can be 0. All the alphas must be equal to 1. That means mod x must be the identity operator. That means x must be unitary. So the extreme points of Mn, the unit bar of Mn, is just the unitaries in this case. Let us try to do the same kind of trickery using prove in general, if M is a one-dimensional algebra, I want to say x is an extreme point of M, of the unit bar of M, if and only if any guesses. There was one case where we saw that they were exactly the unitaries in M. Huh? unitary. So it is easy to see that the unitaries are extreme, but not every unitary is extreme. What about isometry? See, actually, this goes back to the following thing. You must ask what are the. See, you look at the Hilbert space and you take its unit bond. The Hilbert space, you know, is reflexive. Right? That means it is weakly compact. So the unit ball is going to be weakly compact. So you can ask again what are the extreme points of the unit ball of Hilbert space. And the Hilbert space, the geometry is sufficiently nice. One guess. What would the extreme points of the unit ball of Hilbert space be? Huh? But what is special about this basis? What's wrong with this basis? Look at suppose H is C2 or H is C, let us say. What is the unit ball of C? It is the closed unit disk. What are the extreme points there? All points to the boundary. So this is actually going to be unit vectors, right? And we'll call it the sphere of H. So this is what one needs to do. See, if X is an extreme point in so this is what I'm saying. No, I'm trying to prove to you that any isometry is going to be extreme. If uzi is a unit vector for every unit vector, suppose you can write u as an average of two things, then uzi will be an average of two vectors. Now Hilbert space has this nice geometry that says that if a point on the unit sphere is an average of two things, one of those must be inside, one of those must be outside. Inside the sphere, inside the ball. One must have norm less than one must have norm bigger than one. Or at least one of them will have norm bigger than one. So what I'm saying is, it cannot be the case that something on the unit sphere is an average of two things which are again in the unit sphere. The unit sphere does not have any lines in it. There are no flat pieces. So that is what you should use to show that any isometry is actually. So in general, what is true is that if an isometry is extreme, what about the adjoint? The adjoint of an isometry, if something is extreme, then clearly the adjoint is also extreme, right? So the adjoint of an isometry is not an isometry unless it is unitary. Like the shift, right? So you should have isometries, also co-isometries. Somebody whose adjoint is an isometry. Co-isometry is the adjoint of an isometry. In fact, when M is B of H, that is the correct description. X must be an isometry or X star must be an isometry. That includes unitary also, of course. So in general, the partial isometry. And let me illustrate what I was trying to say earlier. That's how we will prove this thing. So what do I have to prove? Suppose, so let us prove this way. Suppose this is true. Then let me take its Fourier decomposition. So what do I want to show? I want to show that what does it mean to say that X is a partial isometry? Huh? Yeah. So we want to say that mod X is a projection. So to prove, what does it mean to say mod X is a projection? What does it mean say about the spectrum of mod X? Projection. Yeah. This is what you want to show. You know that X is in the unit ball, so mod X is in the unit ball. So you know that you know, well, you may not have this, you know that this is contained in 0, 1. Okay, we know this, but we want to prove this. So if mod X is not a projection, that means there will be something in the spectrum which is not 0 or 1. Or equivalently, see, to say mod X is not a projection is equivalent to saying that 1 sub zero 1. So this is assuming that X is the unit ball. I'm assuming it has norm less than equal to 1. I'm saying it is not a projection precisely when the spectral subspace for the open interval must be 0. or 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 that this is the zero operator. Right? Because to say it is here means that one sub closed interval 0, 1 mod x is identity. See x in M1 implies that one sub closed interval 0, 1 of mod x is the identity. You want to prove you're trying to say the spectrum is contained here. That means the difference must be zero. Sorry?
You said mod x is not a projection if mod x is a projection.
Sorry. So to say that mod x is a projection means that this indicator 0, 1 of mod x must be 0. So to say it is not a projection means that this is not 0. If and only if there exists epsilon such that see, note why epsilon. I can even take there exists n, so there 1 over n to 1 minus 1 over n. See, the point is that the union of these intervals, 1 by n to 1 minus 1 by n, is the entire open interval 0, 1. So, if these intervals increase to that whole interval, then the soup of these projections will be that spectral projection. So this sequence of projections will converge to 1, 0, 1 of mod x. So if this is not 0, then one of these must be non-zero. Now if one of these is non-zero, huh? No.
Below is less than equal to negative function of 0. So if below is non-zero, then above is also.
Right. But now from this I want to conclude that whenever this happens, x cannot be extreme. But the function, you must learn to respect this functional as functional calculus. What does it say? See, from 1 by n to 1 minus 1 by n. See, what is mod x? Mod x is a functional calculus corresponds to this function t. Okay. And then we call this f naught t equals t. This is f naught of mod x. Okay. Now, so I'm saying that in the space of functions itself, this function will be an extreme point in the space of bounded functions. You see, if this is not zero, everywhere, see, notice that f naught t is in that interval. So I can look at the function, I can take a function f naught t plus or minus epsilon. Look at the function g plus minus of t equals this for t in epsilon 1 minus epsilon 0 otherwise. What does this do? This has ensured that the function g plus or minus are non-negative and less than or equal to 1. Okay, 0 less than or equal to g plus minus less than or equal to 1. And if I take the average of these two, that will be indicator of epsilon 1 minus epsilon t times t. Times f naught, right? But now I can write f naught as I retain the remaining part 1 minus plus 1 times f naught is f naught minus I'm making a mess here. See, basically I'm saying look at the function f naught on this piece. There I've written it as an average of two things. And those two things stay between 0 and 1. And then take the function f naught outside this interval. Then that will give me two functions, f naught outside the interval and inside the interval f naught plus or minus g. That will give me two functions which are distinct from So I'm trying to say that. So this implies. So what I'm trying to say is that 1 epsilon 1 minus epsilon mod x not 0 implies mod x is not extreme in m plus 1. By just applying the functional calculus, You can write the function t as an average of two functions, bounded by root functions. If this thing is this projection is not the zero projection. And so that will show this way. If this is a partial isomorphy, then it is an extreme point. Conversely, if it is an extreme point, then see, for every psi, sorry. Okay, we'll finish it next time.